Welcome back, everybody. In this video, we'll be starting to look at section 3.3, which is on polynomial functions and power functions. So we're going to look at power functions first. So the first thing to do is look at a definition of a power function. A power function is basically a single-term polynomial function. It's a function that can be represented as f of x equal to k times x raised to the p power, where k and p are real numbers, and k is known as the coefficient. P is known as the degree. So some examples of power functions would be like f of x equals 3x squared, or g of x equals 0.2x to the 0.8 power. The coefficient in the first case is going to be 3, and then the degree is 2. For the g of x, the coefficient is 0.2, and the degree is 0.8. So in this section, we'll start by looking at these functions, which are called power functions. They're a number multiplied by a variable raised to a power, and that's their defining rule. Okay. So the first thing to consider is the graphs of the power functions. And the power functions graphs can take basically one of two forms, depending on whether the degree is even or odd. When the degree is odd, you get graphs that basically look like this group on the left. When the degree is even, you get graphs that look like this group on the right. Okay, so let's talk about that a little bit. Let's do the odd degree ones. Let's actually do even degree first. So here we've got graphs of x squared shown in green. That's the lowermost graph, counting from the right to the left. And then a x to the fourth graph in blue and an x to the sixth graph shown in red. So for one thing, you'll notice that all of the graphs pass through the origin. And the reason for that is that if you raise x to the 0 power, you're always going to get 0. So if you pass 0 to one of these functions, you always get 0 for an output. The other thing to note is that each of these functions is an even function. You remember from an earlier section we talked about even functions. These have degree that's even too. We talked about even functions and how on an even function they have a y-axis reflection symmetry. So their graphs are going to all possess that property that they have that y-axis reflection symmetry. For example, our h of x is the x squared function. We know that h of 7 and h of negative 7 are both equal to 49, right? So for opposite x values, they have equal y values, and that manifests in the graph having that y-axis reflection symmetry. For the odd degree functions, they also pass through the origin because, again, when x is 0, the y will be 0 also, so they will also pass through the origin. And then instead of having the y-axis reflection symmetry, they have the rotational symmetry with respect to the origin. So an example of that would be the x cubed function, which is f here. So here f of x is x cubed. We know that f of negative 5 is negative 125, and that's the opposite of f of positive 5. Okay, and so these are all odd functions, of which that just illustrated one of them. They have 180-degree rotational symmetry. In order to talk about these graphs and their behaviors, there's a particular notation that's going to be helpful going forward, which is an arrow notation or an arrow infinity notation. And it basically is a way of describing the behavior of the graph for certain values of x. So to see that, we're going to look first at the odd functions that we just considered. If you were going to try to draw the graph or describe the graph to somebody, let's say you're on the phone with somebody and you're trying to tell them, okay, well, how does the graph of x cubed look? Okay, well, you say, okay, maybe as x increases, the function values also increase. and there's no limit to that, right? It keeps going up forever and ever. How you would write that is you could say something like, as x approaches positive infinity, which is a way of saying x increases forever and ever and ever, x approaches positive infinity, the f of x's approach positive infinity. Okay? Going in the other direction, as x approaches negative infinity, now we're looking towards the left end of the graph. As x approaches negative infinity, what's happening to the f of x's? Well, they're going down this time. As x approaches negative infinity, the f of x's approach negative infinity. Okay, this arrow and infinity notation is just a way of describing how the graphs are behaving. This is true of the odd power functions. Let's see what we can say about the even power functions. So for the even power functions, as x approaches positive infinity, f of x does what? It approaches positive infinity also. As x increases without bound, the f of x's will too. And then as x approaches negative infinity, we're going towards the left end of the graph, the f of x's this time, they're going up. As you look, as x decreases without bound, as x gets smaller and smaller and smaller, the y values will grow towards positive infinity. Okay, so that is the arrow notation for describing the graph. We'll see some more examples of that as we proceed through this lecture. Okay, what we were just looking at is the end behavior of these graphs. So that's kind of what we just saw is formalized in this table. So let's take a look at what it says. So if you're looking at a power function, kx to the p is your f of x, then depending on the k and the p, that will determine what the graph looks like. First of all, if the k is positive, we're in the top row of this table. If we're looking at an even power, that is our degree is even, then both ends will be up. If it is a negative coefficient, both ends will be down when it's an even power. For an odd power, when it's positive, the right end is up and the left end is down. For a negative coefficient, when it's an odd power, the left end is up, the right end is down. So there's two parts to this really. The coefficient, let's actually take the exponent first. The exponent, whether this is even or odd, that tells you, are the two ends going to do the same thing or two different things? You'll notice when it's even power, the two ends do the same thing. It's either both up or both down. When it is an odd power, it's one up and one down, one up, one down. When it's even, both up or both down. And then once you've got that, if it's positive or negative, that's telling you which way basically it's going to face. For the positive even, it's both up. For the negative even, it's both down. For the odd power, it's and positive coefficient, it's going to be right end up, left end down. For negative, it's going to be left end down and, left end up and right end down. Okay, so that will be the end behavior for a power function, and it's dictated by the coefficient and the exponent. Okay, so let's see a couple of examples. And let's go with Okay, so here's a couple of power functions. We just want to write the end behavior for each of these. So for 2x cubed, because it's odd, the two ends will do two different things. And since the coefficient is positive, it will be right end up, left end down. For the second one, 7x to the fourth, because this 4 is an even number, they'll both do the same thing. Since it's negative, it will be both down. For 6x to the eighth, since the 8 is an even number, both ends will do the same thing. Since the 6 is positive, both will be up. Finally, negative 7x cubed, this will be both ends doing different things because it is an odd exponent, and since it's negative, the right will be down and the left will be up. All right, so I want to add to that the arrow notation that we were describing. So let's see how that will look. All right, so I've added the arrow notation for the first two. As x approaches positive infinity, the f of x will approach positive infinity also for the first function. As x approaches negative infinity, the f of x will approach negative infinity also for that first function. For the second one, negative 7x to the fourth power, we have both ends doing the same thing, going down. So as x approaches negative infinity or positive infinity, the f of x's approach negative infinity. All right, so if I were you, try the last two, see if you can write down the arrow notation for both of those. All right, so this has so far been a quick look at power functions. We want to move on next to looking at polynomial functions, which are built out of power functions. So first, definition, what a polynomial function looks like. So a polynomial function looks like this. Let n be a non-negative integer. So 0, 1, 2, 3, 4, 5, and so on. A polynomial function is a function that looks like this. A sub n, x to the n. So the a sub n is a number, a real number. X is our variable, and then n is an exponent. And then plus, and then dot, dot, dot just shows that the pattern continues. We have a2x squared, a1x, and then a0. So what you can think of a polynomial function as is a sum of a bunch of power functions. Okay, so some examples are shown here. F of x is 3x squared minus 5x plus 1. That's a polynomial function. G of x is 5x cubed plus 2x squared minus 7x plus 4. Another polynomial function. Okay, each of the a sub i's is the coefficient and can be any real number, but a sub n can't be 0. Each product is called a coefficient, and a variable raised to a power is a term. So to use the word there, 3x squared is a term. It happens to be what's called the leading term. Leading term means just that it's in the front. The 1 is called a constant term because, of course, it doesn't depend on the variable. Okay, the second polynomial, 5x cubed, is the leading term. So you'd call 5 the leading coefficient. Sometimes that constant term is also called the constant coefficient. For the degree on a polynomial, we had degree on a power function. For the degree on a polynomial, it's just the highest of each of the individual terms' degrees. So this 3x squared minus 5x plus 1 has degree 2. Okay, for the second one, its degree is going to be 3. Just the highest of the exponents you see on the individual terms. Okay. All right. So we did that already. When you write the polynomials terms in descending order like this is called standard form. Not very meaningful name, but that's the name. It's also sometimes called general form. where each of the terms is listed out by degree. So an example that is not in that form is if you had, say, 3x squared plus 5x cubed plus 7 minus x. Okay, there the terms should look to you like they're all jumbled around. Okay, so that wouldn't be in standard form. We kind of like standard form or general form just because it's easy to tell or keep track of what the highest degree is as well as what the other degrees are. So typically we prefer to have terms written in that form. All right, that will take us to the end of this video. We're going to continue with section 3.3 in the next video, and we'll be looking at the end behavior for polynomials. Okay, let me know if you have any questions, and have a great day.